Okay, so we finish chapter 4 with some more results. Now that we have proved the capacity of the DMC, discrete memoryless channels, we can consider a few more cases. In particular, a model that also has some relevance is the so-called channel with feedback. So what is a channel with feedback? The channel with feedback is that we augment the model of before by a feedback that brings back the output through a one-step delay. So the encoder at time I has not only the message, but also the observation of the output up to time I minus 1. So you may imagine that now the encoder can adapt its transmission depending on what the decoder has received, because the encoder knows what the decoder has received up to a given time. So at every time I, we let the input of the channel xi depend both on the message but also on the output of the channel up to time I minus 1. So we have a strictly causal feedback. Okay? So this system is more complicated because we cannot really consider a pre-ordered codebook and just simply pick one row corresponding to the message we want to send, and this is all already determined because the transmission system is adaptive. So we define the code, a feedback code, as a sequence of encoding functions fi for I equal to 1, 2, 3 up to n, where fi maps the message and the received sequence up to I minus 1 into an input symbol, okay, in this way. So this makes things conceptually much more complicated. We do not have a prefix codebook. The codebook, in fact, is defined by the sequence of encoding functions, which means that depending on what the channel does, whether it is misbehaving, introducing a lot of errors or not, the encoder can essentially cope with the dynamically and with this sort of adaptively to the channel behavior. Okay. Now it turns out that well, okay, just to mention, this model is sometimes is referred to as Shannon feedback because it was introduced by Shannon, and this type of feedback is a very idealized feedback, right? Because we have this sort of magic feedback channel that simply take output symbols and bring them back. In practice, when you have point-to-point transmission with some sort of feedback protocol, well, there is also a communication channel in the reverse direction, such that the receiver can inform the transmitter on what's going on. For example, you can have what is called an automatic retransmission request, or IRQ scheme, for which the decoder tries to decode, and then if it's not able to decode, will ask for more symbols to the encoder, and this by sending back, an acknowledgement or a negative acknowledgement, which means send me more symbol because I cannot really figure out what the transmitted message is, right? So that's a very idealized version of what actual closed loop protocols do in terms of error control. However, there is an interesting thing here, that this theorem 16 that says that for discrete memoryless channels with feedback, the feedback capacity is equal to the non-feedback capacity. So in other words, feedback does not increase capacity of memoryless channels. In order to prove this, well, the achievability, who cares? We can just ignore the feedback. For sure, we can achieve this quantity as before. So all what we have to prove is the converse. If the converse says no feedback codes exist with vanishing probability of error and rates above this maximum mutual information, then whatever the feedback can do, it will not improve capacity. So it turns out that the proof of the converse holds verbatim, which means line by line, also for the case with feedback. If you look at the way I have written here, it turns out that at this point, let me underline this with the color green. At this point, xi in the feedback case is a function not only of the message, but also the message and the received sequence up to i-1. So this step works also for the case with feedback, and then the last step also works. Okay, so this proof applies to the case with feedback and without feedback. And the key here is that the channel is memoryless. So once I condition with respect to xi, I can eliminate everything else due to this fact. That's the key. This is where we use the memoryless property. It turns out that without this memoryless property, this result, theorem 16, is not true. In general, for channels with memory, feedback increases capacity. Okay? But for memoryless channels, feedback does not increase capacity. So what is the benefit of feedback for memoryless channels? Well, it turns out that for memoryless channels, feedback does something very nice, which is called improves reliability. So improves the behavior of the probability of error for finite n. Remember, we have proven capacity by showing that there exist codes with vanishing probability of error for n going to infinity. But we don't really care how fast this probability of error goes to 0 when n goes to infinity. It may go to 0 very slowly. So a more refined analysis of the probability of error using different tools, you can bound the probability of error much more precisely and analyze how fast the probability of error goes to 0 for good codes. And one can show that this probability of error goes to 0 with, in an exponential way with respect to the block length n. And there is the exponent is called the reliability function of the channel, depends on the rate, and depends on the gap between the rate and the capacity. So there is a trade-off. If you want to work very, very close to capacity, then you need very, very long codes because the probability of error, this reliability exponent is very small. So 2 to the minus n times this exponent goes to 0 slowly. If you back off from capacity a little bit, then your probability of error goes to 0 faster. Okay? It turns out that when you have feedback, this reliability exponent becomes much bigger, which means for the same target probability of error, a channel with feedback can achieve this target with much shorter block lengths. And now if you have heard, for example, about low latency transmission, which is one of the claims of 5G. They say you need low latency. Well, what does it mean, low latency? It means that to transmit a message, it has to be transmitted fast. The decoder must make the decision fast. Why? Because, for example, we want to use the transmission channel to control a cyber-physical system. For example, you have autonomous car, and you want to send commands, for example, for road safety, or you want to control a robot through a communication network, and you have, in the control loop, you have this communication channel. If this introduces a long decoding delay, then is introducing a delay in a control loop is not good, because when you send a command, well, something has already happened, so the system can go into instability. So it is essential to have low latency. Low latency and high reliability are enemies for what I'm saying before. Long block lengths means low probability of error. So having a probability of error that decreases very fast with the block length is very useful to achieve low latency. And in this case, one can show that the behavior of the probability of error for channel with feedback, although you cannot beat the capacity in the memoryless case, but you can still improve a lot the behavior of the probability of error for all rates strictly less than the capacity. So it gives you a better trade-off between probability of error and block length. Okay, so, but in order to see this, you need much more refined tools that we are not really going to develop in this course, because otherwise the course would be too long and I want to cover other topics. There is a whole different type of analysis of the probability of error that is able to characterize these reliability functions, these error exponents, which is a little bit more complicated, and then one can also work out these exponents for the case with feedback, and then you can see the benefit of feedback in terms of error exponents. Okay, maybe there will be, I don't know, a project can be on that. We will see when we talk about the end of semester projects. So this is what I say. Feedback may greatly simplify operations and achieve a better behavior of the probability of error versus n at fixed rate, strictly less than the capacity. So just to give you a stupid example, stupid actually is a very, very nice example. Let's consider a super simple case of the binary erasure channel with automatic repetition request. So the channel with feedback would be like this. We have a BEC, right? 0, 1, 0, question mark 1. We send our xi, we receive yi, right? And then here is the delay. So the decoder does the following. The encoder does the following. Here, these are the information symbols, so 0, 1, 0, 0, 1. We let xi to be a new symbol if the previous symbol is non-erased, because it means that the previous symbol was received correctly. And we repeat the current symbol if there was an erasure. So we know if there was an erasure because we see the symbol received at time before. If it is a question mark, it means that the previous transmission was erased, and so we just repeat it, right? So that's a super simple. There is basically no coding. It's just repetition. It's an adaptive repetition. Erase, repeat. Non-erase, move forward. What is the rate of this scheme? Now, clearly, at the end, all the bits will be received, because if you have an erasure, you keep repeating until you eventually do not have an erasure. So how do I analyze the rate of the scheme? Well, the rate of the scheme can be analyzed by the number of successfully received bits per unit time, right? But this is exactly a renewal reward process that we have already encountered. Every time you move to a new symbol, that's a recurrent event. The system resets, and you keep repeating, 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 then non-erasure, move, and so you can on the time axis, you may imagine that you are repeating the current symbol for a certain amount of time, let's say t1, then you move to the second symbol for an amount of time, say t2, which is random because it depends on the erasure. So let's represent it in a different length. So this will be t2. And then repeat the third symbol for an amount of time t3. and then you have T4, and you keep going like that. So each of these repetition times is geometrically distributed, because with probability E, you repeat, with probability 1 minus E, you move forward. So for example, the probability that T1 is equal to K, where K is an integer, is the probability that you have K minus 1 erasures, so it's E to the K minus 1, times 1 minus E, right? So that's a geometric distribution. So we can compute the average number of received bits per unit time simply by the renewal reward theorem. We get 1 bit at every occurrence of the recurrent event. So it's simply, our rate will be the reward 1 divided by the average transmission time. So the mean recurrence time. Okay, so what is the mean of a geometric distribution? A mean of a geometric distribution with a success probability. Success means the event that makes you stop. 1 minus E is 1 over 1 minus E. 1 over the success probability. So we get 1 minus E. And this is exactly C, if you remember, is the capacity of the BC. So this very simple adaptive repetition with feedback gives us rate equal to capacity for this case, which is amazing, right? We have a super simple scheme that requires no coding, just adaptive repetition that can work at capacity, right? That's very nice. And this is just an exemplification of how feedback can simplify your life if properly used. And this is also, if you want, a hint of the fact that most protocols that do error control have some form of acknowledgement and closed loop feedback in some way in order to make sure that the receiver eventually receives what it's supposed to receive. Okay? Good. Okay, another topic, another related topic is the transmissibility of information sources through noisy channels. So now we put together data compression and channel coding. So the problem is the following. We have a stationary ergodic information source with a certain entropy rate. Say, let's make it simple. Sorry, I said stationary ergodic. Let's say a discrete memoryless source with a certain entropy. Let me write it here. This is discrete memoryless source. So a DMS. And we have a discrete memoryless channel. And then we want to basically transmit the source through the channel. And we define something called the compression ratio of the transmission, which is how many channel symbols n per source symbols we want to use. So when this tau is very large, it means that every source symbols will be transmitted over many channel symbols. When it's small, we can squeeze more source symbols into the same channel symbol. So putting together these two things, basically we define a source channel code as a map that maps sequences of length k of the source into code words of length n of the channel. This will be the encoder. And another map that maps sequences of length n at the output of the channel back to sequences of length k of the source, and this will be the decoder. Okay? So these two functions define a joint source channel code. And we define the probability of error as the probability that the decoder decodes a sequence, a source sequence different from the actual source sequence, and the encoder, well, okay, I said it in a bad way. Is the probability that the decoder makes an error given the source sequence average over the source sequence. So this can be also written as sum over all possible v of p, v, k, v, probability that the decoder y n is different from little v, given that the input xn is equal to phi of v. Okay. Good. So we say that the source is transmissible over the channel with compression ratio tau if there exists a sequence of joint source channel coding with k going to infinity and n equal to tau k, such that the probability of error goes to 0. Okay? So the theorem says that a discrete memoryless source V is transmissible over the discrete memoryless channel x, py, xy with compression ratio tau if the following condition holds. The entropy of the source must be less than tau times the capacity of the channel. And conversely, if the entropy of the source is larger than tau times the capacity of the channel, the source is non-transmissible, which means there is no joint source channel coding scheme with vanishing probability of error as the block length of the source becomes large. How do we prove this result? For achievability, we use a special scheme which is called source channel separation. So we can construct a joint source channel code in a separated way. How? We take a data compression code. So here is the source, right? An almost lossless fix-to-fix compression scheme that takes source sequences, maps them into, for example, binary messages, and this will be the source part, and then an encoder that takes binary messages and maps them into code words. At the receiver, we first decode the binary messages and then map back the binary messages into source sequences. So basically we create the source channel code by composing a data compression code for the source and a channel code that works for generic messages. Okay? So we need a fix-to-fix almost lossless compression because, well, B has to be a message of a fixed length, because then otherwise, if it is a variable length, we don't know how to do the decoding, the encoding here, okay? So what happens? Well, we know that we are going to make an error in the encoder or in the source encoder if the source sequence is non-typical, because we index all the typical sequences. So if the source sequence is typical with respect to the typical set of the source, then that source sequence can be encoded, and k times h of v plus epsilon bits are used to encode the sequence. Otherwise, we declare error. For the channel part, we choose a sequence of capacity achieving codes with rate arbitrarily close to capacity. And we know that so all what we need is that the number of bits per code word must be greater than the number of bits produced by the source encoder, greater or equal, so we can map all the outputs of the source encoder into code words. And we also know that the probability of error of these of the channel decoder is smaller than epsilon. So what happens is that now we can simply do the following. We can say, okay, so with this condition can be verified if, of course, we choose, C minus epsilon, which is a lower bound on the rate, times n must be greater or equal than k times h of v plus epsilon. So everything included, we find that by dividing now everything by n, we find that c must be greater than k divided by n, which is tau times h of v, and then we have a quantity which is tau epsilon, and then here we have another, oopsie, what happened? Okay, and then here, from here and here, we have another tau epsilon, so 2 tau epsilon, okay? But 2 tau epsilon is a vanishing quantity anyway, so we conclude that as long as, oh, sorry, I had to, I had to divide by k because tau is defined. Sorry, I got confused. Divided by k, not divided by n. So I have tau here, c minus epsilon greater than h v plus epsilon. And so I have that h of v must be less or equal than tau c minus tau epsilon minus epsilon. So this quantity is as small as we want. So the condition is that if h of v is less than tau c, then we can find an epsilon for which this is true, and then we can find this, we can construct this source channel code by composing an almost lossless data compression code with a capacity approaching channel code. Okay, this is called the separation approach, and proves the achievability, proves the fact that the source is transmissible because we have explicitly constructed a scheme that achieves small probability of error for whenever the entropy of the source is less than tau times the capacity of the channel. For the converse, we let the decoded source sequence at the decoder denoted by this v hat k, and we assume that somebody gives us a scheme. Now, that scheme cannot be based on separation. It is any scheme, because in the converse we have to prove the non-existence, so we cannot make any assumption of the given scheme. The only assumption is that the probability of error goes to 0. So by Fano inequality, we have that the conditional entropy of what we want to detect given what we have, this is the output of our decoder, is less or equal than 1 times the probability of error times the size of the alpha beta word we want to detect. Now, the alpha beta word we want to detect is a sequence of length k over the alphabet v, so the cardinality of v to the k is simply cardinality of v to the k, take logarithm, and you get k log v, log cardinality of v, where v is the alphabet of the source. Now what happens? Now we assume that there exists a sequence of codes with compression ratio tau and vanishing probability of error, and then we simply work out these inequalities. The source is memoryless, so the entropy of the source is just 1 over k times the joint entropy of a sequence of length k. Now, adding and subtracting, basically adding and subtracting this conditional entropy, we see that this minus this gives us this mutual information, and then we have this term, but this term is upper bounded by finite inequality, so we get this upper bound. And now we use data processing inequality. We have vk, the encoding function, was it phi or psi? Oh, okay, the encoding function was phi. Okay, the encoding function phi, we have xn, we have the channel yn, and then we have the decoding function vk, and we have that the mutual information from here to here is less or equal than the mutual information from here to here, because this chain of operations form a Markov chain. So we can take this mutual information, upper bounded by this, multiply and divide by n. So now we have n over k makes tau, and then we have 1 over n, right? And then what we have at this point is that 1 over n, the mutual information between the sequences, is less or equal than n times the capacity. Why is that? These sequences are induced by the code. These are n-letter sequences induced by the code. But because the capacity maximizes each, the channel is memoryless, and the capacity maximizes the mutual information for every marginal. So in other words, explicitly you would write here, apply the chain rule with respect to x, and you have that you get this. And then each of these terms is less or equal than c, okay, because c is the max of this for the distribution over I. At the end, we end up with this bound. Now this epsilon, this quantity here, call it the epsilon k, probability of error goes to 0, 1 over k goes to 0 as k becomes large, so this is a vanishing quantity. So we end up with saying that h, if such code exists, then h of v must be less or equal than tau c plus a vanishing quantity, which concludes that if such code exists, then h of v must be less or equal than tau c. So altogether, this means this gives us the transmissibility condition, and we have proven that for h of v less than tau c, we can construct separation codes for which the source is transmissible, and for whatever code we can imagine, the condition h of v less or equal than tau c is necessary. Okay, so this concludes the proof. There is one interesting aspect here, which says the following. If I have to map a source into, I have to transmit a source through a noisy channel, this result shows that separation is optimal. So in terms of transmissibility, concatenating a very good data compression code with a very good channel code is a very good thing to do, okay? Because in fact, it achieves the transmissibility condition. There is no penalty, at least asymptotically, for very large block length. And this is called, some people call it the Shannon separation principle, or Shannon source channel separation principle. Now, although this is not entirely true, because again, when you do things jointly, you can do a little bit better, or maybe even much better for small block length. So again, when you look at the performances for low latency, things are not like that. But let's look just the asymptotics, so like a first order approximation of the problem. This means that effectively we can focus on compressing sources with some techniques that depends only on the source, and transmitting information through noisy channel with some other techniques that depends only on the channel. We put these things together and we get an optimal scheme. This is really nice because it says essentially that, you know, we have many sources in the world. We have, you know, computers, we have TV, we have radios, we have voice, telephones. Okay, and then we have a big network that is able to transport bits. Let's call it internet. And this theorem essentially says that it's actually essentially optimal to take all these different sources, convert them into bits, and then just find efficient ways to deliver the bits to destination. And this is actually pretty much optimal. Now, although this is not really true in a network sense, because this we have just considered a simple transmission situation with one source, one channel, and going from the source to the destination. This gives us a principle that actually, in most cases, doing things optimally, like treating these things separately and then joining them together, is not such a bad thing to do. And this somehow just is like the philosophical justification of what is called the network convergence. So today we have data networks, video streaming, audio streaming, telephone, voice calls, video conferencing, Zoom, etc., etc. They all work over the internet. They all over IP. Okay, voice over IP, video over IP, streaming over IP, video conference over IP, etc., etc. This is because essentially converting everything into bits and delivering the bits and reconverting back at the destination is a very good thing to do. In the old days, we had TV broadcasting, use certain analog or whatever systems. Then we had telegraphs, we had telephone, analog telephone to optimize to carry human voice, etc., etc. Every different source had a dedicated special network. But in fact, this is not needed. When you convert everything into bits and you deliver the bits, you are pretty good. And this is the separation principles that allows effectively the modern digital era, when everything is over IP. We have a single layer of bit transport and delivery, on top of which we can construct all sorts of services. Okay? So the philosophical implications of the separation principle are very deep and very important. Another topic that I want to introduce here is capacity cost functions. So we can slightly complicate a little bit the problem of channel coding by introducing a cost in using the channel. For example, power. Maybe every transmitting symbols costs some power, and you are interested also in bounding the transmission power, right? So in general, we define a cost function as a mapping B from the input alphabet to the non-negative reals, for which the cost of an input sequence X is simply the average cost per symbol, 1 over n times the sum of the cost of the symbols, Bxi. Examples may be Hamming weight costs. Hamming weight is a cost function that costs 1 for non-zero symbols and 0 for zero symbols. For example, if you have a binary transmission and you transmit packets of photons, you transmit 0, you transmit nothing, so it costs nothing. You transmit a packet, a 1, you transmit a packet of photon, it requires a certain energy, so it costs the cost of this energy. Other example is quadratic cost. Quadratic cost, when the input alphabet is a subset of the real numbers, we may be interested in the energy of the signal. So if x represents samples of a discrete time signal, we know that x squared is related to the energy of those samples. So oopsie, what I did, the quadratic cost, it directly gives us something that is related to the energy per symbol that we are transmitting. Okay? So the capacity cost function, for a given cost, we want to find what is the best possible rate, the best possible achievable rate. So the problem is, now we have also an additional constraint. Our code has to satisfy the constraint that for every code word, the cost per code word must be less or equal than some fixed cost. And therefore, we can define C of B as the supremum of all achievable rates for codes that satisfy this cost constraint. And the theorem, capacity cost function for DMCs, says that for a given channel and a given cost function, the capacity cost function is the maximum of the mutual information, where the maximization now has a constraint. It's not over all possible input distributions, but it is over all input distribution with average cost, so expectation of B of x, which means sum over little x in the alphabet of Px of x, B of x, less or equal than B. So we introduced a cost constraint in the maximization problem of the maximizing mutual information. Okay? So I'm going to go through the achievability and converse proof, maybe in one of the live sessions, because otherwise this lecture becomes too long. The proof is not difficult. Is just a slight variation of the proof that we have already seen, where we have also to control the probability of the event that some code words may not satisfy the cost constraint. So we have an additional term in the error term, additional term in the error bound, that takes into account the probability that the input sequence does not satisfy the cost constraint. We will go through this in the live session. For the converse, it is essential to prove a fundamental property of the capacity cost function, that the capacity cost function, seen as a function of the cost, if I plot here the cost B, and this is C of B, the capacity cost function is a function that is monotonically non-decreasing and, oopsie, there's something wrong here, monotonically non-decreasing and, oh my goodness, what am I doing? Okay, monotonically non-decreasing and concave. So it satisfies Jensen's inequality if you take any two costs, B1 and B2, the segment joining the capacity cost function is always below the function. Okay, this sort of monotonically non-decreasing is obvious, because if you make this constraint larger, then you can only enlarge the set of probabilities over which we are maximizing, so the result can only, certainly will not decrease, so the monotonicity is obvious. For the concavity, we have to work a little bit, but it's also easy to show. Okay, so that's a general property of the capacity cost function. It's always monotonically non-decreasing and concave. And once we have this property, then we just work out final inequality and prove the converse. So we have also examples if you want to see. These examples are not, we will go through in the live session, because again, it's a little bit tedious. What I want to say here now at this point is to spend a couple of words on how to compute capacity. So focus, focus on the problem maximization, which is a convex maximization. And in particular, I will consider the general problem also with the cost constraint. So we have the whole picture. Okay, if you don't have a cost constraint, just remove it from the problem, and you will get the unconstrained capacity for infinite cost, if you want. Okay, so how do we write this problem mathematically? Well, we define the channel through its probability transition matrix. So what is this? Well, PRS, where RS are two indices denoting input and output letters, is simply the probability that y is equal to S given x equal to R. Okay, so in other words, this is P y given x of S given R. Okay, so without loss of generality, we can index the letters of the input alphabet with integers, index the letters of the output alphabet with integers. We call these integers R and S, and we define this matrix, as we have already done, is the transition probability matrix. And then we have a probability vector of the input, which is P. Okay, and then we have a probability, a cost vector B. What is B? Where we define here PR is the probability that X is equal to R, and B sub R, the art component of B, is simply the function B applied to the art letter of the alphabet. Okay, so now from the definition of mutual information, we see that the mutual information can be written in this way. A very good exercise is go back to the various ways of writing mutual information and see that in fact you can write it in this way. The average cost is simply this, summing over all input letters of probability times cost, must be less or equal than B. These is a constraint that says the vector P must sum to 1, and this is components are from 0 to 1, so these two means P is A, P, and F. Okay? This is the cost constraint. So this is a maximization problem where big P is fixed because it's given by the channel. The optimization variable is small p, so is the vector P, and those are the constraints. This is a convex maximization problem because the function, we have seen the objective function is concave in the vector P, and therefore we are maximizing a concave function, and the constraint set is a convex set because it's basically just limited by hyperplanes, right? So it's a probability simplex cut by a half space given by this inequality. Okay? So what you can do is take this problem, write it in CVX, put it into MATLAB, and solve it. For a given probability matrix, you will get the capacity and the corresponding probability vector. However, this does not exploit the property of the problem, and so here we present an algorithm that in fact exploits the property of the problem. So it's nice because it's not a general convex solver, it's something that works for this problem explicitly. So in order to do this, we consider the following. First of all, we consider an auxiliary conditional probability matrix defined again on the alphabet X and Y. Let's call it Q, which generally is different from P. Okay, and then let's take the constraint set of all probability vector P satisfying the cost and being probability vectors. We call it calligraphic P. So this is the constraint set, and we know that this is a convex set. Okay. Then we consider a different function that instead of mutual information I call it J, function of three objects. The probability vector P, that is the optimization variable, the matrix, transition matrix of the channel capital P, which is fixed, and then we have this auxiliary other probability matrix Q, okay, and we define this function in this way. So this seems like a complication because we have introduced these new variables, so we have augmented our problems, but it turns out that one can show that the capacity cost function can be given as a double maximization of this function. Is max over the probability vector P, max over the probability matrix Q of this new function. And in addition, for fixed P, the maximization with respect to Q can be given explicitly. For fixed P, I can find the optimal Q. For fixed Q, the maximization of J minus lambda times the average cost can also be given explicitly. Okay? So, why we do this? We do this because this double maximization, when you fix Q, maximize with respect to P, and then fix P and maximize with respect to Q, it turns out that this double maximization probably converge to the optimum. And since we have explicit partial solutions, then you have just to alternate these two steps and you will converge to the optimum. And this is the Blehat-Arimoto algorithm. Okay? It is an alternating maximization. So we have a double maximization, but there are special cases where maximizing with respect to one variable by fixing the other one, and then fixing what we have just optimized, optimize with respect to the other, then redo, 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 iteratively, is called alternating maximization, converges to the optimum. It's not always true, by the way. It's true under certain conditions. We will see later the condition for which this is true. Let's first prove the theorem. So first of all, we want to prove A. In order to prove A, it is sufficient to show that the maximization with respect to Q for fixed small p and big P give us the mutual information. Why? Because once we have the mutual information, then the outer maximization will give us the capacity cost function. Okay? So what we do, we let Q star SR to be this specific choice. Question, is this a conditional probability distribution of the output given the input? Yeah. Let's see if it is true. I mean, for the input given the output, sorry. It's true because, let's see, this term, this numerator is P of x equal to R, comma, y equal to S. So it's the joint probability of RS, because this is Px, Py given x. And then the denominator, when we sum over all r's, this is simply P of y equal to S. So this effectively is P of x r given y equal to S. Okay, so that's a conditional probability of the input given the output, and D is the denominator, because we are marginalizing with respect to the first variable, to the x variable. This is a distribution of the output, right? And then it turns out that by definition of the mutual information, this can be also written in this way, because this is the joint distribution, and this is Px given y, and this is Py, and this is simply Px comma y. So that's another way of writing the mutual information. And then if you take the definition of the J function and you write it and you replace to Q, you replace this Q star, you find that this is exactly the case. The two coincide. So this proves point A. Then but this doesn't prove already the result. We want to prove that the maximum of this is equal to the mutual information. So we have to show that for any other choice of Q that is not Q star, we get something that is less. So we take this difference, right? And replacing the explicit expression, we find that this difference can be written in this form, which can be written at the end as a conditional divergence, because this is divergence between the conditional distribution for given S, and then you are averaging out with respect to S, which is the y variable, and this is a conditional divergence, and therefore is non-negative. So this shows that okay, that choice of Q star makes the J function equal to the mutual information, and any other choice of Q will give you something that is smaller. So this proves that the max with respect to Q of J is the mutual information, which is what we wanted to prove. Then we have to also, well, this proves also point B, because point B says that Q star in this form maximizes the J function for fixed P, but we have shown here that that's exactly the point. So we have this explicit form, right, which is exactly the form we wanted to prove. So B is proved. We need to prove C. In order to prove point C, we consider the Lagrangian function for our optimization problem. The Lagrangian function, we have the objective function minus the lambda, the constraint, and times the constraint for the cost, minus another Lagrangian multiplier mu times the sum constraint to 1, and then we have the non-negativity constraint that we treat using the KKT conditions, as I already explained. Basically what we do first is, for this partial Lagrangian function, we find a stationarity point. So we differentiate with respect to Pj, which is the jth component of the vector P, and we find this object. And the KKT conditions say the following: this derivative must be non-negative. It has to be equal to 0 if we have a stationary point P star J strictly inside the domain, or it may be non-negative if our optimum P star J is at the boundary, so is equal to 0, because in this case the maximum is obtained at the boundary, and therefore the condition is that the derivative starts off with it must be non-positive. Okay, so then we try to solve the stationarity point and see if we get a solution P star that is always positive, and then we accept it. Otherwise we have to discuss what happens to the boundary. So solving the partial derivative equal to 0 with respect to Pj, we find this solution. Okay? And at this point, all what we have to do is to impose this constant here, which is exponential of -1 minus mu. We want to impose that the constraint that the sum is 1 holds with equality, and this means simply that we divide by the sum over all j's. So this will be the P star j, and of course, being a ratio of exponential over a sum of exponential, this is always strictly greater than 0, and therefore we can accept it. We have found our stationarity point. Okay, so this is the explicit form of the maximization with respect to a probability vector P of that partial Lagrange J minus lambda times this. Because the rest, you see, we have just added a constant here, and this imposes the fact that we have a probability vector. So that's exactly what we want to do. So this proves point C. And now the Blair-Hartley-Harimoto algorithm simply consists of alternating these two steps. So notice the following. In general, I should determine the Lagrangian multiplier lambda in order to impose equality constraint on the cost. But this is difficult to do because you have to plug this probability in here, solve for lambda, and impose this, right? Normally, when we have this type of Lagrangian problems, it's much easier to fix the Lagrangian multiplier, do the optimization for a fixed Lagrangian multiplier, and then the Lagrangian multiplier will give you a value of the cost. You repeat this for many values of the Lagrangian multipliers, and then you have the whole function in parametric form. In other words, instead of fixing B and find C of B, you can also fix lambda and then find in parametric form C equal to C of lambda, B equal to B of lambda, and then you have C of B in parametric form, and the parameter is precisely the Lagrangian multiplier. So that's a general approach when we have this Lagrangian optimization. Is typically much easier to use as a parameter the Lagrangian multiplier as a knob. You turn it, so you make it small, you make it large, and you get the whole curve of C as a function of B in parametric form. Okay, so in this case, we do exactly as follows. We fix lambda, and then you repeat this for many values of lambda, so in order to have the whole trade-off. And then we simply start from an initial probability vector, for example, the uniform probability, call it P0, and then we iterate from P, get Q, from Q, get the new P. You keep iterating these two until convergence. At the end, our C of B will be the value, the asymptotic value after many iterations of the J function at P infinity, capital P Q infinity, where infinity means many iterations, and the corresponding cos B for that lambda will be given by this. Okay? Now you, as I say here, we obtain the capacity cost function in parametric form, where the parameter is the Lagrangian multiplier lambda. Now, why this algorithm is proven to converge? You know, this theorem does not necessarily imply the convergence of this alternating maximization, especially starting from any initial point. But there is a general result, that says, well, this double maximization has a spatial structure. Oopsie. This double maximization has a spatial structure because the problem for fixed P and Q, capital P and capital Q, this function J is concave in P, and the constraint set here is convex. So we are maximizing a concave function in P over a convex set. Then, for fixed capital P and small p, the function is concave in Q. So when we have a double maximization where with respect to each individual argument fixing the other one, the problem is convex, it turns out that this alternating maximization, which is exactly what Blechach-Harimoto does, can be proven to converge to the optimum. Okay, so that's a general result. When you have a convex problem, and you are maximizing, or if the function is concave in both variables, fixing the other, we maximize. If the function is convex in both variables, we minimize. Anyway, alternating maximization, alternating minimization converges to the optimum. That's a general result, a very powerful result. Every time you can break an optimization problem by introducing maybe auxiliary optimization variables, like in this case we had to introduce this Q because the maximization over P alone is difficult to do, but if we have now two variables, P and Q, and the problem is convex, we can start doing alternating maximization, and each sub-problem becomes easy to treat because we have an explicit expression here. Now, for a given P, we have the optimal Q. For a given Q, we have the optimal P. We alternate these two, and the problem converges. I mean, and the algorithm converges to the optimum. So that's the general result, and this is the Blechach-Harimoto algorithm. If we have time, maybe on Thursday, we are going to see maybe an example of this. But I have to, it's very easy to program in MATLAB, but it requires a little bit of time. Or maybe I will post an exercise in MATLAB that you can do. Okay, so that's the end of the chapter, and I'll see you in the live session.